So here we are, machine learning. We are down to chapter 9, unsupervised learning. I was very interested in this, as I have been in all this. I've been racing ahead much more than I usually do in my classes, as this topic is of great personal interest to me. All right, so unsupervised learning, we've talked about it before. Currently, do we have a way to distinguish between AI-generated music and human? No. This is actually a very good question. We do not have any way to identify AI-generated anything. There are several tools out there that claim they can identify AI-generated writing and images, and they've been proven to be very ineffective. Although OpenAI announced this week that they are developing a tool that will generate AI-generated content with 99% accuracy, but it is not available yet, and no one knows if that's going to work. So that is a very important question. Many people are struggling with it for many reasons, but as far as I can tell, for the foreseeable future, there is going to be no practical way to tell whether something is AI generated or not. The only thing is sort of like forged paintings. If you do a really bad job of it, there are people who can spot the errors. But if you do a good job, I think you can easily make AI generated content that will fool almost everybody, where nobody's really sure. And the current tools to detect it are so bad that they will even flag non-AI generated content as AI generated. So they're sort of worse than useless. All right, so supervised learning is where you have data with labels, like you have a bunch of handwritten numbers and you know what the right numbers are, so you can train based on that. But most data doesn't come already labeled. Actually, if the data was already labeled, why would you even need machines to do machine learning? What you obviously want is machine learning that can detect handwritten labels that somebody's handwriting that haven't been labeled yet, and that sort of thing. So it's mostly unlabeled, and usually the only way to label them is to get human workers, and that's expensive and drudgery work. So unsupervised learning is working with unlabeled data, and you can do a lot. For example, as we already talked about this, dimensionality reduction, where you have a picture with thousands of pixels and you want to boil it down to say just the 10 relevant features that matter for this task. That's a task you do just by finding out the variance and finding the principal component that captures most of the variance, and you don't need any labels for that. Clustering, where you just group it into clusters. These ones are over here, these ones are over here. That doesn't require labels. Detecting anomalies, which find where most of them are and find the ones that are outliers. And density estimation, a similar activity, determining the probability density function of the data. These are all things you can do without labels. So we're going to talk about clustering algorithms, k-means, which is beautiful and simple and very easy, and then db-scan and Gaussian mixtures. So classification versus clustering. On the left, we had a classification task, which is the iris task we talk about. There are 3 different species of irises, and you can identify them by petal length and petal width and another number not included here. And so you see you want to separate them into these 3 categories by color. That requires labels. That's classification. But clustering is here. You could take that data, remove the labels, and then cluster it. And then, of course, all you're going to get is 2 clusters. There's clearly a cluster down here and a cluster up here, and there's nothing about this data to make it easy to tell that this should be further split into 2 groups. So you'll get some of the information just by clustering without labels, and some of it you wouldn't get without the labels. So here's some clustering use cases. Grouping your customers into clusters. You might want to say which customers are willing to pay a higher price, which customers demand an unusual size of garment, and things like that. And then you can adapt your product marketing to them. You can do data analysis to group your data into clusters and then analyze only one cluster at a time. This is the sort of thing you might do in voting databases. First, form people into groups. Now figure out why do the black people want this and the suburban people want that and the inner city people want that. That's how they do voting predictions. Try to figure out, break people into groups of some kind and then figure out what each group wants. Dimensionality reduction, like we've said, you can do it with principal component analysis, or you can do it with clustering. You can find clusters, and then you can measure each instance's affinity with the cluster, which is basically the distance to the center of the cluster, and then you can replace every instance with just its cluster affinities. So if you go back to here, you had petal length and petal width. But once you've found the clusters, you could instead just rate everyone by how far they are from the center of this cluster and how far they are from the center of that cluster. And those would be 2 numbers that would again represent the data in a different space. And this might lower the dimensions. Here it's 2 dimensions this way and 2 dimensions the other way, but in principle this could be 100 dimensions, and if you had 2 clusters you just go down to 2 numbers, so that's one form of dimensionality reduction. And again, like all the dimensionality reduction techniques we talked about, the point here is to take the input data, which is far too complex, and remove the unimportant information from that data and keep only the important information. And if the only thing you care about is which category it's in, then just the distance from the center of the category might be the important information and all the rest the unimportant. Then there's feature engineering. Like we just said, the cluster affinities might be useful as features, even if you're not going to throw away other features, that might be useful. And to detect anomalies. All you have to do is find instances that don't seem to be tied to any of the clusters, and those are your anomalies. You can then have semi-supervised learning, which we're going to do, where some of the data is labeled, and clustering turns out to help a lot in propagating the labels to the unlabeled instances. Search engines can work this way. Search for images similar to the reference image and just return those. Image segmentation, you can cluster pixels various ways, perhaps by color, to find the objects in a scene. So k-means is this exciting, wonderful, simple technique. I was very charmed by it. So this has been older than I am, came out in '57. So here's some data. We have 5 Gaussian blobs, 3 blobs here, and then 2 blobs with a bigger standard deviation over here. So there are 5 groups of data. And the way k-means works is incredibly simple. You are hoping to find an answer like this, where you find the center of the blobs, and then you minimize the distance to the centroids. This is how it works. So k-means will you have the centers of the blobs, and then you choose the nearest blob. So that means you get these decision boundaries, and as you can see, it's not perfect. In particular, up here, these ones, which really belong to the yellow blob, are going to be join this one because it happens to be closer to that one. So you can see a flaw with k-means. When the blobs are not all the same size, then k-means doesn't work perfectly. It assumes that I should split this at the halfway point, whereas a smarter system would notice this is a tighter blob, so I should really split it over here, not over here, but it's not that smart. However, k-means is simple and it converges fast because it's very simple. So there's 2 ways to do it. You can either assign each instance to a single cluster, or you can give it a score per cluster, which is, let's say, be sort of a percentage of belonging to each cluster. Either way is fine. So if the original data was 2-dimensional, you replace it with 5-dimensional data, which is the distance from each centroid. So in this case, it increases the dimensionality, but if the original data had more than 5 dimensions, this would be lowering dimensionality. So here's the algorithm. It's incredibly simple. Randomly place the centroids, then label the instances by finding the nearest centroid, then move the centroid to the center of the instances in that class, and that's it. Then just repeat. So you start with random centroids, and so over here you've got this, that gets all this gray area joining this one. So now you calculate the center of mass of this gray area and move over there. So you guess at random, you get some data around there, and then you move to the center of the data you've captured. So it's extremely simple. If you think about it, it's very much like gradient descent, sort of falling down a hill. And then you do it again, and this turns out to converge quite rapidly, as you can see, to a pretty good solution, clustering the data. So to get the score, which is the number to measure how good this is, you do the sum of the squared distances from a centroid, and then you negate it so that you're maximizing it instead of minimizing it. So here you have a bunch of data that's pretty far from the centroid, so this is a bad solution. And here the data is much closer to the centroid, either that one or this one, so you'll have a smaller sum of the squares, which is an improvement. Now, one problem is if you have bad enough luck with the initial centroids, it might converge to a bad solution. Like here, it put one X down here. It made one centroid for both of these and this, and then it sort of split this in half. So that's a bad solution. If you start with an unlucky initial centroid, it can converge to a local minimum. It's not really the best minimum. Here's another one where it puts 2 of these together and 1 for both of these. And so again, those are less than optimal solutions. And so by default, it will try 10 times and take the minimum, the best solution it can find after 10 random starts, which in practice turns out to work very well. All right, if the data has clusters, and it's then the computational complexity is linear in the number of instances because you just have to add up more distances, linear in the number of clusters and the number of dimensions. If the data lacks a clustered structure, though, this model can fail to converge. If there isn't any real clustering, then it'll just randomly move the centroid and then randomly move it and randomly move it, just keep moving it forever and not get anywhere. But in practice, it's one of the fastest and most successful algorithms. So I wrote one with just random data to try to create this. So I've left the code here in case anybody cares. I didn't bother to put it in the project. But with just completely random data and 5 centroids, I tried converging with 100 dots. And you see I got completely different solutions here. And here's the score. This is the number it's trying to maximize. This one is minus 25.1. This is minus 25.2. So as you can see, both of them are about equally good at fitting these 100 random points that really have no clusters. Here's 1,000 points. So the score is minus 305, minus 311. And again, you can see quite different shapes. And here's one with 10,000 points. And again, you get various random solutions. Here's minus 3,100, minus 3,200, showing you it does settle now on something, but of course there's no way to really decide there's a right answer when there really are no clusters. All right, so k-means plus was an improvement proposed in 2006 that just chooses the starting centroids not completely randomly, but makes them inclined to be more distant from one another, because I think you can see one of the obvious flaws in the ones that fail are you'll put 2 centroids near each other, which basically cancels them out into one centroid. You get the ones that fail. Here's the ones that failed. Like over here, you got 2 near each other, and this one you have 2 near each other. So having the centroids 2 next to each other is likely to lead to a bad solution, so this avoids that. And that is now the default system used by the k-means implementation we're using at these Python libraries. And there's another one. You can have an accelerated k-means, where if you want to accelerate it, you can use the triangle inequality to estimate distances. Because, for example, if you want to have the distance between an instance and the center of the cluster, you could calculate it, but that might be a long calculation if you have, say, 100-dimensional data. But if all you have to do is figure out that it's further than this one, and you can sort of estimate the distance without recalculating so many distances. You can take known distances to other points you know about. I think that's the point. And therefore, you can get a measure of distance that's good enough without bothering to do the whole calculation just to make it faster. And you can also do mini-batch k-means, which is the same thing we've talked about many times. If you have too much data, then you only use part of the data for each iteration and move the centroids just slightly each time, and that can speed it up, and that amounts to a lot like stochastic gradient descent, where you move towards the solution and you only use part of the data to guide you there just to make it faster. And that would let you use huge data sets. So here's an example of one showing the inertia, which is a measure of the total distance that you're trying to make smaller. And as you can see, k-means and mini-batch k-means both converge quite nicely, but the mini-batch has much less training time, so it's faster and seems to reach just as good an answer. So the one problem we haven't talked about is how do you choose how many clusters? More clusters means lower inertia, even if it's overfitting the data. If I have 3 clusters, then it'll fit. But if I have 8 clusters, it'll get even smaller, and I can just have as many clusters as I want. You can cover this with centroids and make the distance very small. So if you plot the inertia versus k, it will go down, down, down. Now, we know the right answer is 5, but see, 4 is almost as good, and so you can try to find this sweet spot where further numbers of clusters don't really help you very much. It turns out that the best way to do that is this thing called a silhouette coefficient. And that's a number that varies from -1 to 1, +1 if it's well inside its own cluster and far from other clusters, -1 if an instance is assigned to the wrong cluster. And so now you can see there's the silhouette score. It has a clear peak at 4, and 5 is almost as good. So it's amounting to about the same thing as the other technique, but this is considered a good way to determine the best number of clusters. So here's the limitation of k-means. If the clusters have varying sizes, it doesn't work so well. If they have different densities, it won't work so well. For example, if I had 1,000, let me go back to one there. If I had, say, 1,000 dots here and only 100 dots here, then since it's just adding the square of all the distance, it will take, I got to fit these 1,000. That's far more important than fitting these 100. So if there's different number of dots in each cluster, it will weight the one with more dots much more than the one with less dots, and that's probably not what you want. That's a limitation. If they're different sizes or non-spherical shapes, then it's a problem. Like right here, this cluster that's got this linear shape, it's measuring an error. So it's going to regard this distance as bad of a problem as a point being way out here. And that's not really fair. If you had a smarter model that could actually follow the shape of the cluster, it would understand that these dots are all well fit, but one out here is not well fit. So just taking the distance alone is not the best measure of error. And that's why, again, this non-spherical shapes are a situation where k-means won't work very well. And you'd have to do something like scale to get rid of that, or switch to Gaussian mixtures, which we'll talk about later, which can fit more complicated shapes. All right, so you can do image segmentation. You can do it by color, where you just find pixels with different colors and assign them to the same segment to find objects. You can do pixels that are part of the same object, if you have some other way to determine what an object is. This is, I guess, what Teslas are doing. You know, I would like to test the image accuracy of a Tesla recognizing things. I wonder how badly a Tesla fails if you, say, wear a green shirt walking around in a forested area. Is it more likely to not notice you and think you're a tree? I would think it is. And then you can have instance segmentation to pick the pedestrians out, all the pedestrians as a group or the individual pedestrians. Here's an example of doing it with colors. You have an original image of a ladybug on a dandelion. And if you lower it down to just 10 colors or 8 colors and then do color segmentation with k-means, you see even taking it down to just 8 sections, you've still captured pretty much a lot of the image. If you go down to 4 or 2, then you're losing it. But 8 is pretty good. You have a couple different kinds of yellow, a few different kinds of green, and you have the orange for the ladybug, and it pretty efficiently finds them. Is it fair to say one goal of k-means is to get clusters of plus or minus the same size? Yes, that's a fair statement, and ignore. That's what, now probably what you'd like is something that will just find clusters, but what k-means does is it finds clusters assuming they're all the same size and shape. That's an issue. So you would have to try and scale your data somehow to make that all about the same size and shape, or your k-means will not be the optimum algorithm. Then you can do semi-supervised learning, which we're going to do in the project. So they got another one of these data sets of handwritten numbers with 1,797 images with labels. And what you can do is just ignore most of the labels. So if we just keep the first 50 labels, which are what you see here, and try to predict them all just from the first 50 labels, we can see how it works. So if I train, right, so I label these by hand, I could train just from the first 50. And it turns out that training just from the first 50 doesn't get a very good job, but what you can do is you can use k-means to separate them into groups. And these are not just the first 50, pardon me. There, here we go. There, that's what I'm, okay. So you start here. Now, if you fit a model using all images and labels, you get 90% accuracy or more. That's the whole data set with all the labels. But if you just take the first 50 instances and train just from them, you're only 75% accurate, which makes total sense because, you know, you only have 50 instances instead of 1,700. So what you do is you use k-means to form 50 clusters. And now you take the images close to the center of each cluster. And now you have found images that match each type of image. So this is like you have 10 digits and you decide, well, there's probably 5 different ways to draw one. I'm going to get the best example. Here's a one with a hook on it. Here's a one that's too thick. Here's a one that's kind of skinny and bent. Here's a straight one. Here's a one that looks kind of like an L. So it turns out there's like 5 different ways to write a one, and I've now found them, and here's the representative examples of these ones. And so you found 50 categories, and you found 50 representative images, which are in the center of each group. And now you label these by hand, and these are the most representative of the group. Then you train your model on the representative instances, and now you get up to 85% accuracy instead of 75% accuracy because you've carefully chosen the most representative images to train on. But you can do even better. You can take those instances and now you can propagate labels to all the others by propagating to all the clusters. So now you add in labels that were artificially generated, and that gets your accuracy up to 89%, which is almost as good as the 90% training on the original labeled data. And you can do even better yet. You can say some of these propagated labels are probably wrong, so I'm going to remove the 1% of outliers, which is, again, an unsupervised learning task, and now we can get up to the same 90% you would have got from the original data. So that's really a very nice process to show how this will work. That's how you could handle unlabeled data and find an efficient way to propagate labels to the unlabeled. So here's the summary. If you train on the data with all labels, you had 91% accuracy. Train on the first 50 is 75. Train on 50 representative images after clustering gets you to 85. Propagating labels to all images gets you to 89. And removing the outliers gets you all the way back up to 91. So then you could improve it with active learning. You could have a human expert interacting with the learning algorithm. It could train it on everything it has so far, make predictions, and then it could pick some of those instances and present it to the human for labeling. Choose the ones with the most uncertainty, or the ones which would result in the largest model change, the ones that are most critical for the performance of the model, or the ones that different models disagree on, that sort of thing. You take some of them and ask a human to sort them, and you iterate this until the performance improvement is no longer enough to justify continuing going. This is what theoretical physicists, I used to do this for years, they would call this a stable point. You cannot prove that you found the right answer, but you have proven that this method is not going to change anymore. So you call that a stable solution. That's often what you have to do in complicated situations where you can't really have a model that works very well. Could this tech be used in a post office to recognize the mail addresses in 1990s which had very limited computing power? Well, that's the issue, Sue. As you look at the history of machine learning, these techniques are very old, but in practice, I don't think they became practical until we had GPUs. I'm not sure of this exact procedure here, but next time we'll talk even more about this, how we talk about how this happened. There were waves of interest in machine learning. Like I say, I did this many decades ago, and it came through several times and just fizzled out. As it sounded good, but in practice it didn't turn out that you could build anything worth having for any reasonable amount of money. And am I getting some of my scripts and code from Bard? Well, I'm not. Although I am slowly learning to use Bard to help me get over problems. I don't think I have this week, but last week I did. Every now and then I'm stuck on something and ask Bard for help. So far, all I've been doing is making modest changes in the Python from the book authors, and I've been able to figure that out myself. But when I get stuck, I do ask Bard more and more. I highly encourage everybody to ask Bard or ChatGPT, or probably the best one for code is Claude 2. We should all get used to using AI to help us do our job all the time. Anyway, let's try a Kahoot. These are good questions. I had a student come for help from one of my office hours, and I think I surprised him by just taking their question and throwing it in Bard, but I think we should all get used to that. We should get used to using AI to help us with whatever we're doing. All right. All right, so which task requires labels? Right, classification. You can't sort them into classes without having examples that are sorted into classes so you know what classes you're looking for. All right, which situation makes k-means fail? Yeah, the blobs have different sizes. The borders between them will not be placed in the optimum place. All right, what value is useful for choosing the number of clusters? The silhouette score, which is a number which measures how much each instant fits neatly in a cluster and is not arguably placed in a different cluster. That's something that will be best when you have the right number of clusters. All right, Greg. Boot. And ant ignore. All right, good. All right, let's go back to the slides, which are here. Okay, so let's talk about some other techniques besides k-means. dbScan is density-based spatial clustering of applications with noise, and what this does is just find a region of high-density instances and follow it where it goes. So count how many instances are near it in a neighborhood. If it has at least a certain number of samples in its neighborhood, then it's in a dense region, and all instances in the neighborhood of the core instance belong to the same cluster. So, and an instance that's not a core instance and doesn't have one in its neighborhood, that's an anomaly. So if you have something like the moons data set we've used before, it can follow these densities. If you have the right epsilon set, then it will follow this region of density and call this one cluster and call that another cluster. Now, if your epsilon is too small, then it will follow this cluster but then be fooled by a region of low density here into breaking into a separate cluster and a separate cluster. And so your book gets upset about the fact that it sorts this into like 10 groups instead of 2. And I can see why you might not like that, but I wouldn't regard this as useless. The 10 groups still follow the data and could be used. But anyway, that shows you how it works. It just tries to cluster together regions of uninterrupted high density. Then there's agglomerative clusters that form clusters like bubbles and sort of tries to combine them like bubbles merge. Birch, which is designed for very large data sets, and this can be faster than k-means. And during training, this builds a tree structure with just enough information to assign new instances to cluster. Then mean shift starts with a circle centered on each instance and shifts the circle to center on the mean of the clusters inside, so it sounds very similar to k-means that way. Keeps going until the circles stop moving, then combines them to form clusters. So unlike k-means, it can then follow clusters of any shape. And the only hyperparameter is the circle size, the bandwidth. So it sounds like it would amount quite similar to what dbScan did. All right. Affinity propagation. I haven't explained exactly how this works. The instances exchange messages and somehow elect exemplars, which are going to be like those representative samples we had in that problem earlier. And then each exemplar and the instances that selected it are the clusters. So now you find clusters of different sizes, and so it's sort of like our elections, where people elect for a candidate and then they join a party, and now you've sorted your thing into groups. So they say it is complex, so not that good for large data sets. Because this exchanging looks like every instant has to exchange with another instance, and that's going to be like order m squared, and the number of instances squared. Then there's spectral clustering that makes a similarity matrix between clusters to reduce dimensionality, which sounds rather like principal component analysis, and uses another clustering algorithm like k-means in that low-dimensional space. So that's another way to do it. All right, and then we'll talk about Gaussian mixtures, where you assume that your data follows Gaussian patterns. So I got some code here that makes it. You make Gaussian distributions. Here is one that has the x and y correlated, and another one where the x and y are correlated, so you have a long skin Gaussian here and a long thin one here, and I think a round one over here. So there's 3 different clusters that are Gaussian, and you do expectation maximization. Initialize cluster parameters randomly, assign instances to clusters, and you update the clusters to match the data you've captured, sort of like k-means. It's a generalization of it, allowing varied cluster shape, size, and orientation. So like k-means, it can converge to poor solutions, and so you ought to repeat it several times. And it can work like this. to fit that data I just showed you. See, it does a good job. It makes a nice curved a tilted Gaussian here and a tilted Gaussian here and a round Gaussian here, which is pretty good for that simple data. You have various hyperparameters to control this. The covariance type determines how much the different sizes are allowed to have different shapes. Different clusters allowed to have different shapes. So spherical means they all have to be symmetric x and y, but they can have different sizes. Diagonal means they can be ellipsoids, but they have to be vertical or horizontal, I think. They can't be tilted. Tied means all ellipsoids must have the same shape, size, and orientation. And full means no constraints at all. And it looks to me like this is a full fitting. It's perfectly happy to have a round one here and tilted ones there of different sizes. So it's full options available here. And so here is what tied would do. They all have to have the same shape and the same tilt. So you fit this one with the tilted one, even though it's not best. Here's spherical. They all have to be round. Since they have to be round, you can't fit these ones worth a damn. So it's split it into two, this way and this way, which is, like what k-means, original k-means would do something stupid like that, because it regards this diagonal distance here as just as important as distance off here. So it's just not going to follow that data very well at all. All right, and then you can do anomaly detection. Any region instance in a low density region is an anomaly, so these stars are the anomalies, the asterisks in this plot, the ones that just don't seem to fit into any of the clusters. And so you might do this to find defective products on an assembly line, for example. All right, so to select the number of clusters, there are theoretical information criteria you can use, like Bayesian information or Akaki information criterion. I don't know how to pronounce this. And they are basically entropy. They're some kind of measure of probability and a log of probability, the log of the likelihood function. And so these numbers are minimized for the right number of clusters. So it is in the same general terms as that number we had up here. The silhouette score is the same kind of thing. If everything is nicely sorted into a cluster and it's not close to being in a different cluster, then you have a high silhouette score. And this measure of entropy here, of something that looks like entropy to me, Bayesian information and Akaki information, has the same general property that if things are really nicely sorted into categories, you get a minimum value, and otherwise, if you have the wrong number of clusters, you get a higher value. And as you would expect, having too few clusters is really bad, and having a few too many clusters only modestly increases this, because of course you could take a cluster and split it in two and you still have approximately the same amount of order. I think that you would always want to use full so you do not have to worry about the shape of the clusters. Well, Greg, that's just the same as always. If you have too much freedom in your model, you might fit the noise in the model instead of the trend. All these are hyperparameters. So the reason you have hyperparameters is to smooth the answer. If you give your model more freedom, you will get a lower error, but you might be fitting the noise. Like I can see a sort of trend here where there's sort of a stripe this way and a stripe this way. So splitting this into 3 diagonal clusters might be a little better than one round one, but that's just because of randomness in the data. So technically you would get a lower error here, but it wouldn't generalize. When you tested it on the test sample, not the training sample, it would be worse. So that's the part that's kind of an art more than a science, where you add these extra conditions which make the immediate fit worse, but make it more representative of what you think is the real trend. All right, and so you can have Bayesian-Gaussian mixture models where you have you can set the n components to a large model value. Like I said, this is a model that you can set to a large number, and it will automatically eliminate unnecessary clusters. So for the 3 Gaussian cluster model, it worked. For the moons, it did this. And see, notice the moons have a sort of gap here, like a gap in somebody's eyebrow. And they have sort of a region of high density here and low density there. And so it was fooled by those into breaking these up into 2 groups instead of 1. So that seems to be almost an unescapable logical issue. In fact, it looks like it split this into 3 groups along here too. So, it ended up with more categories than just 2 out of this data. And that seems to be something that would be quite difficult to prevent. All right, Then there's something called fast MCD, which is useful for outlier detection. It assumes the inliers are from a single Gaussian distribution and classifies the others as outliers. This seems like the simplest thing to do. Just assume that everybody is in one group, and anybody that doesn't fit in that group is an outlier. Isolation forest. You build a random forest. This is pretty cute. Randomly pick features and thresholds that will sort your data in half, split it in half again, split it in half again. So you keep chopping until each instance is alone, and then you just decide how many generations of chopping did it take to isolate that instance. And the ones that got isolated earlier are the ones you call the outliers. That seems like a fast, clever, pretty smart technique. Then there's local outliers, where you compare the density of instances to a density around its neighbors and see which ones have less neighbors, and that makes them the anomalies. One class support vector machine. You map the instances to a high dimensional space and use a linear support vector machine classifier. And this amounts to finding a region that encompasses all the instances in the original space, and anybody outside that region is an anomaly. So just a fancy way of drawing a sort of border around the instances. And then, of course, you can use what we did before. You do principal component analysis and dimensionality reduction, and then reconstruct the images and look at the reconstruction error. We did this last week. You can take a 784 dimensional set of images and lower them down to just 23 dimensions, and then rebuild them, and you get images that are pretty close to what they should be, but there's an error. And the ones with high error are the outliers, the ones that actually had a lot of variance in the dimensions that were not considered important. So, various ways just to find outliers. Any kind of statistical test will do. And I must say this is quite common in threat hunting. There's one common issue when you're doing a network monitoring, where you say, I want to find the network traffic that is out of the ordinary. And normal network traffic is very random appearing anyway. So this is an issue. How do you define what's an outlier? And there are various ways people try to present graphs in the SOC to somehow see some kind of graph that will make it easy to spot which one of these things is not like the others. And that's what this general topic reminds me of. The people have been trying to sell machine learning network monitoring systems for quite a while, yet I have not seen any studies of how well they work. But certainly in the next few years, we are going to see all sorts of security devices based on techniques like these, where it somehow detects which one of the machines on your network is doing something unusual that appears to be bad, suggesting that that machine is undergoing an attack or somehow doing something suspicious. It's also, they try to detect human behavior that's suspicious. Those products are already out there to try to detect which humans in your company appear to be disloyal because they're doing suspicious things. And I'm sure they're using similar techniques to this, but I think right now they don't work very well. Let's try another Kahoot. All right. All right, so what algorithm finds outliers from reconstruction error? That's it, principal component analysis. You find a small number of components that capture most of the variance, and the ones you can't reconstruct from that are the goofy ones that don't fit in, the outliers. All right, which one has continuous regions of high density? Yep, dB, which I'm pretty sure is density based. Let me just flip back to that. Yep, density based spatial clustering. Okay, that's what it is. All right. All right, which covariance types makes all the clusters the same? That's the tide option. Makes all the clusters the same. They can be tilted and stuff, but they got to all be the same. All right, and ignore. And Greg. And Woot. All right.